All right, let's go over the problems on checkpoint 12. So first question we're talking about, so this function we have is the rate of change of the skunk population on the Pecos campus. So basically we're given a rate of change. So we're given the thing we usually think of as a derivative, and we're being asked to find, the parent function. We're being asked to find P of t from here. So how do we do this? Basically, I need to find an antiderivative. So I want to find an antiderivative for P prime of t with respect to t. So P prime, I'm just rewriting that. So I'm taking an integral or an antiderivative of 300e to the negative 0.01t dt. So I have an inner function here. So I have 300e, and e is raised to something that's not as simple as the input variable t. So what I would like to do is this. I would like to say that u is equal to that exponent, negative 0.01t. So basically if we're setting up a substitution, our goal here is to take our integral, which is in terms of t and dt, and to transform it into an integral that's in terms of u and du. So if I say u is equal to negative 0.01t, then I have to have a corresponding du. So let's do this first. I'm going to take a derivative of u with respect to t. So du dt is equal to negative 0.01, which means that du is equal to negative 0.01 dt. And I'll go one more step here. If I divide by both sides by negative 0.01, then what does that give me? That should give me that dt equals, what is 1 divided by negative? That should be negative 100. Let me make sure I don't miss a factor of 10, because that happens to me sometimes. 1 divided by 0.01 is 100. So dt equals negative 100 du. So now I can use this to transform this integral. So now I'm going to rewrite this integral like this. I'll keep the 300. Draw. Oh, likes to freeze on me. Every week, it freezes on me, and I stall while it wakes up. Or it doesn't wake up for some reason. Oh, there it goes. Lots of integral symbols. I only need one. So the integral of 300 times e to the u times dt, which is the same as negative 100 du, or negative 30,000 e to the u du. So now I have this integral in a form where I can finally take the integral. So the integral of e to the u is something I understand how to do. Think back to the derivative of e to the u. The derivative of e to the u is e to the u, which means the integral of e to the u is e to the u plus c. So this will be equal to negative 30,000 e to the u plus c. Now, do I have enough information to figure out what c is? I should, and here's why. I know that at time equals 0, actually, let's do this first. Let's re-express this. So let's replace u with what I originally said it was, negative 0.01t plus c. So we know there are initially 6,000 skunks on campus, right? So here's what we can do. So this thing right here is P of t. Now, the last thing we would like to do is to figure out what this value of C is. So what I'm going to do next is plug in 0 for T. So I know that when T equals 0, P of T equals 6,000. So negative 30,000 times e to the 0 plus C equals 6,000, which means that C equals 36,000. So there is my expression for P of T. P of T equals 36,000 minus 30,000 e to the negative 0.01 t. So here's my expression for what? So if P prime of t is the rate of change of skunks on campus at any given time, then the integral should give me the number of skunks at any given time, t years after 2023. So that's our expression for P of t under those conditions. So part B, how many total skunks will be born in the next 5 years? So here's what we'd like to do to answer part B. To answer part B, it might seem like all I have to do is this, P of 5, and then we're done. But I really want to compare that against my baseline, because I don't really want to, if I do P of 5, that'll just tell me how many skunks are living on campus in 5 years. That doesn't mean that they were all born in the last 5 years. It's just some of them could be older than 5 years. I don't know how skunks live, not how long skunks live. So I need to subtract off the number that were already alive, and that's the 6,000. So how do I find P to the 5? That'll be 36,000 minus 30,000 e to the negative 0.05, and then subtract that. I'm not going to plug in 0 for P because I know the initial value was already 6,000, right? So 6,000. So what do I get here? I get 30,000 minus 30,000 times e to the negative 0.05. So I'm going to calculate this, but while I do, one thing I want to point out is that in the setup of the question, we were told that there were 300 new births per year, but that rate was declining. So if there were 300 births per year and that was a constant, we would expect there'd be 1,500 skunks born, right? But that rate's declining. So maybe we'd expect a little bit less than 1,500 skunks to be born. So let's see how we do with that. So 0.05, we raise e to the negative 0.05, multiply that by 30,000, subtract that by 30,000. So I get a number of, that based on what I just said, hopefully makes a little bit of sense. The number I got is, if I round to the nearest whole number, I get 1,463. All right. So that is all for question 1. Moving on to question 2. All right. So similar setup, I am given the rate of change of something. And I want to find from that rate of change, like I don't want to use the word volume because it's not always going to be a volume, but like a quantity of something. So I'm given a rate that a quantity is changing, a rate at which a quantity is changing, and from there I want to integrate to get a quantity. So a water tower is leaking at a rate given by this, where T is measured in time. So T is time measured in minutes, and R of T measures the water flow in gallons per minute. So this right here is in gallons per minute. How much water leaks out of the tank in the first 12 minutes? Okay, so I'm going to set this one up a little differently. So this one here, I set up, at no point did I ever set this up as an indefinite integral, or sorry, as a definite integral. I set this up as an indefinite integral. This one, though, I think I can kind of jump right to the definite integral step because I am told, I want to know how much water is going to flow out of this tank. So I'm going to integrate over the rate of change function. But I don't just want to get a function, I want to get a number. And the way I get a number, I have to have limits of integration. So I have to know over what span of time am I going to integrate over. And in this case, it says I want to know the flow of water in the first 12 minutes. So first 12 minutes, that means, all right, if T is the time in minutes since the leak started, then I want to go from 0 minutes all the way up to 12 minutes. So this is the integral that I need to evaluate. This will give me my value here. So another thing that I did in this last problem was we did integration by substitution, and then we substituted back to deal. Basically, we transformed the integral into terms of u, and then we've transformed it back into terms of t. What I'm going to do with this one, I'm going to transform it into terms of u and then never go back. And I just want to do this to kind of give you a look of how both of them work. In reality, if you prefer one over the other, that's great. Yeah, one is not inherently better or worse than the other. But I did want to show you kind of both ways to do this. So in either case, let's set up an integration by substitution. I like to think about what is the inner function at play here. Is there an inner function? I think so. So the exponent to my exponential function is usually a good thing to try first. So u equals 0.05t. I am going to then find that du is equal to 0.05 dt. Now I'd like to solve for dt. How do I solve for dt? Divide both sides by 0.05. So that means dt is equal to, what is 1 divided by 0.05? That should be 20 du. Okay. So now that I've done that, I should be able to transform my integral, right? So let's do that. The integral from 0 to 12. Not quite, because 0 and 12 are t values. So for now, I don't want to transform the whole thing at once, so I'll do this. I'll say t equals 0, t equals 12, and I'll drop in the rest of the integral that I have already talked about transforming into u. 50 times e to the u times dt, which is 20 du. Okay. And then I'll clean this up one time. T equals 0, t equals 12, and the integrand is 1,000. Nope. 10. It was 1,000, wasn't it? You know what? I just made this mistake so much on your last test that I don't trust myself. It's 1,000. 1,000. E to the u, du. Okay, so our integral is almost totally transformed into terms of u. Our last issue here is to deal with the limits of integration. So how do I do that? How do I get those in terms of u? Well, I can use this right here. I have this recipe that basically I made a function u in terms of t. So if u equals 0.05 times 0, that's 0. So that lower limit will still be 0. And then u equals 0.05 times 12. That'll be equal to, I think that's 0.06, but let's be sure. Oh, off by tens everywhere. It's just 0.6. So here's my integral, all transformed, 0 to 0.6 of 1,000 e to the u du. So now we're in a place where we can do this integral. So what's the antiderivative of 1,000 e to the u? So the beautiful thing about, rewriting this integral, like substituting this integral, now this is like the simplest integral there is. Like the integral of e to the u is e to the u. So this becomes 1,000 e to the u, and we're going to evaluate at the limits 0 and 0.6. And I want to emphasize again here, I'm not going to deal with t ever again. I'm going to plug in those limits for u. I'm going to get a number, and we're going to be done. That's not to say, I mean, you could plug t back in and get an answer. And if you do it correctly, you're going to get the same answer that I will. So again, just a matter of preference. So now what does this integral look like? This will be 1,000 e to the 0.6 minus 1,000 e to the 0. So what is e to the 0.6? Times 1,000. So I'm going to round to the nearest whole number. So this is 1822. 1,000 e to the 0. E to the 0 is 1, so that is 1,000. So I get 822 gallons of water. All right, that's all for question 2. And question 3. So I have this function, f of x equals x to the 10th natural log of x. And I also know something about its antiderivative, capital F. The only thing I know about the antiderivative is that when x equals 1, f of x, or capital F of x, equals 0. So how do I get an expression for capital F? I need to integrate x to the 10th natural log of x. So I just used integration by substitution twice. And why did I know I could use integration by substitution? Well, what told me I could use integration by substitution is that basically I had a composition of functions. I had an outside function, which in this case was 300e to the x. And my inside function was like x equals negative 0.01t. Or in here, my outside function was 50e to the x, and my inside function was x equals 0.05t. So that's a composition of functions. I have one function as the input to a second function. That's not the situation I have here. The situation I have here is I have two distinct functions, x to the 10th and natural log of x, and their outputs are being multiplied by one another, as opposed to if I had this, the natural log of x to the 10th. In this case, I would say, all right, my inner function is x to the 10th, and my outer function is natural log of x. So a little bit of compare and contrast. That's not what I have going on here. So I have a product of two functions. I'm trying to integrate them. This is where integration by parts is typically going to be what's called on. So now that we have that, let's remind ourselves how integration by parts looks. So typically, I mean, you've probably seen lots of, equivalent but different looking forms of this. Here's the one that I usually go with. The integral of u dv is equal to uv minus the integral of v du. Essentially, what you're doing here is you're trading the integral you can't do for an integral that hopefully you can do. So what I get to choose here basically is, all right, you get to split up the integral you're given into two parts, a u and a dv. Or another way to think about it is you're splitting up your integral into two parts, one of which you're going to take a derivative of, the other one you're going to take an integral of. So with natural log, I don't really have a good integral or antiderivative for natural log. So I never like to say always to you, but it's a very good idea to try putting natural log of x as your u. So you can take a derivative of it. So if u equals natural log of x, then du will equal 1 over x dx. Because the derivative of natural log is 1 over x. Okay, so if I said that u was natural log of x, that means by default dv has to be x to the 10th dx. Nope, not dx. No, it is dx. Has to be a dx term there. So now dv is the thing I have to integrate to get v. Now what is v? V will be equal to, how does the power rule for integrals work? I'm going to add 1 to the exponent, x to the 11, and divide by that exponent, 11. So here are basically my ingredients for how I'm going to set up this integral. So the thing I was given, I split that up into a v and a u, and I didn't write the dx. So x to the 10th dx is dv, and then natural log of x was u. So now I'm going to do this. I'm going to say this integral, the integral of x to the 10th natural log of x dx, is equal to uv. So uv is going to be 1/11th x to the 11th natural log of x minus the integral of v du. What is v? V is 1 over 11 x to the 11th. What is du? That is 1 over x dx. So this is kind of the bargain. I traded the integral I was given for an expression that had another integral in it, that hopefully that integral was more digestible. Let's find out. So this, I don't have to integrate. I can just take this with me. 1/11th x to the 11th natural log of x. And then I can simplify this a little bit. I believe this becomes 1/11th. Nope. The integral of 1/11th x to the 10th dx. Is this integral something I can do? Yeah, I can. This is essentially product rule again. Product rule, not product rule. Power rule. So I can do the power rule again. What I'm going to do here is I'm going to add 1 to the exponent. So it'll become 11, and then I'll divide by 11. Basically, I did a very similar step not too long ago. So what's that going to become? 1/11th x to the 11th natural log of x minus 1/11th times 1/11th x to the 11th plus c. So here's what we have so far. F of x equals 1/11th x to the 11th natural log of x minus 1 over 121 x to the 11th plus c. So very, very close to done. I believe we're done with the calculus component. So now what remains is to figure out that value for c. So what information do we have? We know that capital F of 1 equals 0. So let's plug that in and see what we can figure out. So if we plug in 1 for x, we get 1/11 times 1 times the natural log of 1 minus 1 over 121 times 1 plus c, that all equals 0. So this whole term goes to 0 because the natural log of 1 is 0, which means that c is equal to positive 1 over 121. So where do we end up? Final expression for f of x is 1 over 11 x to the 11th natural log of x minus 1 over 121 x to the 11th plus 1 over 121. All right, that is all for checkpoint number 12.